Okay, so welcome back to another video. So in today's video, we have the following. So we want to prove that the integral from 0 to 1 of 1 divided by ln of x plus 1 divided by 1 minus x dx is equal to lowercase gamma, where gamma is, lowercase gamma in particular, is defined as the Euler-Mascheroni constant. Specifically, this is the difference, the limit difference of the harmonic series, and then subtract that with the natural log. We actually did a video like this before of the Euler-Mascheroni constant proof. So, you know, we have another one that exists that we want to show that it equals, the given integral is equal to gamma. So with that, let's actually get started. Let me just define this whole integral that we're given as capital I. So let's see, we have the integral from 0 to 1 of 1 divided by ln of x. And rather, using linearity, I'll actually split this into two integrals. So that means we have thus dx, and then plus the integral 0 to 1 of 1 divided by 1 minus x dx. Okay, let's first focus on this integral over here. Let's start by paying attention for the integral from 0 to 1 of 1 over ln of x dx. Okay, so what I want to do is let's actually do a u-substitution. Well, this time we'll do this in terms of t. Actually, I'll define, let's call x equals e to the negative t. Okay, so that means dx is equal to negative e to the negative to the power negative t dt. And so what that means is that now substituting things back, we get so we have our new bounds. So let's see, x approaches so x is equal to 0. That means this would have t would have to be infinity from the lower bound, and then as x equals 1, that means t would have to be 0. And then we just plug in what we have, dx is equal, so negative e to the negative t, and then divided by, let's see, we plug e to the negative t back for x, we get ln of e to the negative t, that's just negative t dt. But notice that the negatives cancel out, but we have to change our order of integration since infinity cannot be the smaller bound as 0 is the upper bound. So this means is infinity, 0, and then negative e to the negative to the power e, negative e to the power negative t divided by t dt is what we're down with so far. I'll just underline this in black for now, just to recall, well, rather just establish what we have for the first part of the integral. So now let's focus on the second part. So I'll write this in red. So now we want to focus on the integral from 0 to 1 of 1 divided by 1 minus x dx. Okay, so now let's do a substitution. So this means, how about I let t equals 1 divided by 1 minus x. Okay, then dt is equal to 1 divided by 1 minus x quantity square dx. Okay, now, but we want to plug x in terms of t, so I have to solve this equation on this top for a bit. So let's see, I'll just multiply a 1 minus x to both sides. So 1 minus x, then t equals 1. I'll divide t to both sides, so we get 1 minus x equals 1 over t. Then subtract a 1 and then divide a negative 1, so we get that this is x is equal to, let's see, so this will be 1 and then minus 1 over t. Or if I want to simplify this out a little bit, just so we get this whole expression under just one fraction. So this will just be, let's see, t over t, and then so this is t minus 1 divided by t. So with that, I can substitute some things back into here. So we have our new bounds. So let's see, if I plug 1 for x, so this will just be, so it's 1 over 0. So this is actually going to approach infinity. And then if I plug 0 for x, this is just 1 over 1 minus 0, so that's just 1. and then we just plug in the necessary pieces back. So let's see. Oh, and also I'll multiply a 1 minus, I'm actually missing another step from this piece here. So let me move to over here. So I'll multiply a 1 minus x quantity squared to both sides. Let's see, dt equals dx. But I want everything in terms of t on this side, so I'll have to plug what we saw for x back here. So we have, let's see, 1 minus t minus 1 divided by t and square equals dx. Now if I actually just substitute, not substitute, but if I like reduce this to just one fraction, let's see, we get t, here I'll expand this, we get t divided by t minus 1 divided by t squared. And if I simplify this, one sec, I just forgot the dt on this side here. dt equals dx. Let's see, so this is t minus t 0, then that's a positive 1, and then just a t, then square that, we get that this is just, let me move that evaluated answer down below. We get that this is just 1t squared dt is equal to dx. Okay, cool. So then now we have what we need to substitute. So let's see, dx, or how about let's do like this. So it's 1 and then divided by, let's see, 1 minus x. It's just the same thing from here, and then in that parentheses it's just 1 over t. So I'll just substitute that as 1 over t. Okay, and then multiply our dx substitution, which is just 1 over t squared dt. But we can simplify this out a bit to get 1. Well, from the integral from 1 to infinity of, let's see, this is just t, because I just this is under division, so this is just that goes on, the variable t just goes on the numerator, and then t squared dt. But the t's cancel out from the top, so we get that this is just integral from 1 to infinity of 1t dt. Okay, now what I'm going to do now is I'm actually going to break this integral into parts. Why is that? Well, to put it simply, we know that this is an improper integral. It diverges because we have the infinity over here. So to do this, we'll actually set the bound from 0 to infinity of 1 over t dt. And then I'll subtract that with the piece from 0 to 1 of 1 over t dt. So we have these two. So this is what we have so far in terms of simplification. Now I'll just plug that back into what we have in the original equation. So to establish, so far we have that I is equal to the integral from 0 to infinity of negative e to the negative t divided by t dt, and then plus our integral from 0 to infinity of 1 divided by t dt, and then subtract that with our integral from 0 to 1 of 1 divided by t dt. But I can actually combine some things because these two share the same bound, so I can actually just end the denominator as well. So it makes things easier that I can actually just add the 1 back to the numerator. So this means we have the integral from 0 to infinity of 1 minus e to the negative t divided by t dt, and then subtract that with the integral from 0 to 1 over t dt. That's exactly why we actually split the integral here, just to combine some terms together simply. But notice that we're also actually gonna rewrite one more integral as well. Notice that because the integral of from 0 to 1 of 1 over t dt diverges, but you'll also notice that if I were to take the integral from 1 to infinity of 1 over t dt, that also diverges too. So since they're like equate each other the same because they both diverges in this sense, we can actually just rewrite this integral, specifically this term right here. So we have that this is the integral from 0 to infinity of 1 minus e to the negative t divided by t dt, but this time I'll subtract that with the integral from 1 to infinity of 1 over t dt. As you can see, if you were to graph two integrals, when you're looking at the area underneath the curve, the areas are, I know that they diverge, but it's kind of like approximately very similar. I know I shouldn't really use the word approximate, but if you were to compare the two pictures side to side of those two integrals, they're sort of equivalent to each other in a sense. But even though they're both divergent, but we can actually just rewrite some things in a way. I don't necessarily like to use approximate when it comes to this kind of work here, but I'm actually just going to use that reasoning to find that. Okay, so we have this, and I'll just underline this. I'll underline what we have so far in black. Now there's some things that I actually want to manipulate as well. So what I want to do is I actually want to define a little definition, and I'm pretty sure you guys can guess this. We're actually going to define the constant e in the definition of a limit. So we know that e is equal to the limit as n approaches infinity of 1 plus 1 divided by n to the power n. So what happens, let's say if I were to take that exponent with e to the negative t. So we get that e to the power negative t is equal to the limit as n approaches infinity of 1 minus t divided by n to the power n. Okay, so I can use this the limit definition of e and replace this with this equation. So now we get that I is equal to the integral from 0 to infinity of 1 minus the limit as n approaches infinity of 1 minus t to the power, or divided by n to the power n divided by t, and then dt, and then I'll subtract that with integral from 1 to infinity of, this is supposed to be 1 over t. And now something to note from here. Well, actually, not yet. Now, clearly you can see that this integral converges, so that means I can actually just drag the limit outside. So this means I can write the limit and then approach this as n approaches infinity, but I'll replace all the infinities with n. So we get that this is the integral from 0 to n of 1 minus t divided by n quantity to the power n divided by t, and then dt, and then subtract that with, this time this is 0, or this is supposed to be 1, and then n 1 over t dt. But you can clearly see that you know how to calculate the definite integral of 1 over t. So let's see, 1 over t dt is simply just equal to the natural log of t. Evaluate this from n to 1, then that's simply just equal to the natural log of n, since the natural log of 1 is just equal to 0. So I can just replace that with just the limit. It's just the same integral, so 0 to n, 1 minus t divided by n, quantity n divided by t, dt, and then subtract that with the natural log of n. So now to do this, let's actually do a u-substitution. Well, now I'm just gonna call this letter v. So let's see, we're gonna let v equals t divided by n. Now there's a t in the denominator, so I want something to replace t in terms of v. So therefore, that means I'll just multiply n to both sides. So I get that this is n times v is equal to t. But from over here, we take the derivative. dv is equal to, let's see, this is just in respect to t. So this is 1 over n dt. But we see that this is just equal to n times dv, which is equal to dt. And then we can just do the necessary substitution. So let's see, the limit as n approaches infinity of the integral. So we have our new bounds. We plug n for t. So let's see, n divided by n, that's just 1. And we plug 0 for t. So 0 divided by n is just 0. Okay, so we get 1 minus that's v, quantity to the power n. And then replace t with n times v, and then replace our dt with n dv. Okay, but we can simplify some stuff since n from the numerator and denominator cancel. I'm not gonna, well, okay, I'll just write the natural log of n from just as a continuation. So let's see, this is the integral from 0 to 1 of 1 minus quantity 1 minus v to the power n divided by v dv. Now, we're actually going to do another substitution. And you know what? I'm just gonna call this u, because I've been saying u a lot. So let's see, we're gonna let u equals 1 minus v. Okay, so there's a v in the denominator, so I want to replace the v for in terms of u. So this means I get that v is equal to, so let's say I subtract 1, so we get u minus 1, and then divide a negative, so that means we get that v is equal to 1 minus u. Differentiate both sides, so we get that du is equal to negative dv. I'll just divide the negative to both sides, so that means we get that negative du is equal to dv. Now do the substitution another time, so this is the limit n approaches infinity of our new, okay, so we have our new bounds to evaluate. So let's see, if I plug 1 for v, this is going to be 0. And if I plug 0 for v, this is going to be 1. And let's see, we have 1 minus, so 1 minus v is going to be u. I actually don't need that parentheses, actually. And then, let's see, so this will be u, and then to the power n, and then divided by v, so that's 1 minus u, multiply with our negative du. But notice that, same thing, just like from earlier, we have to switch our bounds of integration because you can't have 0 as the upper bound while 1 is the greater number that's part of the lower bound. So we switch that gets a negative, but that negative cancels from that negative du. So we ended up that the integral is positive. So this is 1, 0, 1 minus u to the power n, and divide by 1 minus u du, and then minus ln of n. Okay, cool. And we're almost close to our goal. So if you pay attention closely, this is actually a very interesting formula. So this is actually part of the geometric series of using the sum of the nth term. So this means, so I'll write it over here, using the sum of the nth term of the geometric series, okay, then the formula is defined as follow: 1 minus u to the power n divided by 1 minus u is simply just equal to our partial sum from k is equal to 0 to n minus 1 of u to the power k. Okay, so with that, I can actually just substitute our partial sums back to here. So we write this, so we get the substitution, so the limit as n approaches infinity of 0 to 1 of our partial sum of u to the power k du, and just minus ln of n. Okay, so we can actually just, this is basically the definite integral, so this means this is the limit as n approaches infinity of our partial sum. Let's see, this will be u to the power k plus 1. This is just the power rule. K plus 1, evaluate this from 0 to 1. We see that if we plug 1 for u, this is just 1 divided by k plus 1, and then 0 is going to be 0. So we get that this is 1 divided by k plus 1, okay, and then minus ln of u, or ln of n. And we're just almost done. Now the last thing we want to do is we're going to change our index, simply because we want to show that we have the that gamma is equal to this integral. So change of index. Now I'll change everything from n minus 1 all the way to, so that we get that it's n. So this means we have that the limit as n approaches infinity. Let me write that a little better. That means this will be n on the upper index, and then let's see, k is equal to 0, so let's see. So that means the lower index will have to start at k is equal to 1, and then change the k plus 1, so that means this will be with 1 over k, then minus ln of n, which you can clearly see that's actually equal to the gamma series. So it's the proof complete. And we just draw the box, or rather, I'll just reiterate and say that let's just put down the final conclusion that the integral 0, 1 divided by ln of x plus 1 divided by 1 minus x dx equals gamma. And I'll just put a check as a way that we actually prove that the equality is true. And like so, we have finished this video. And I'm going in this red box. Okay. Ooh, that was loud. That's pretty cool if you ask me.